Okay, so this is our lecture on using a voltmeter and an ammeter and how to put those in a circuit, and as well as a kind of a demonstration of some of the equipment that we'll be using in here: breadboards, power supplies, voltmeters and ammeters, and all that. So let me quickly, yeah, please do come. I think, yeah, come to the last period today. Yeah, we're going to maybe continue. We'll see how far we get in this, but yeah, we will have class today. It probably won't be the full hour, but at least come, yeah. So let me share the objectives real quick. All right, so if you look at objective C.2.D 1 through 3 down here. These ones, students should understand the properties of voltmeters and ammeters, right? And our multimeter is a voltmeter and an ammeter in one. So you can state whether the resistance of each is high or low, right? Does a voltmeter have a high resistance or a low resistance? Does an ammeter have a high resistance or a low resistance? And then identify or show correct methods of connecting meters into circuits in order to measure the voltage or the current. All right, and then assess qualitatively the effect of finite meter resistance on a circuit into which these meters are connected. Yeah, we'll talk about that. That's kind of a secondary thing. Really, these first two objectives here, neatly circle them for you. Okay, so let's go back to the camera. And again, this is a little bit, I brought, this is a new classroom. I brought all the stuff up that I think I'm going to need, and I think I have everything here, but there's a chance that this all doesn't work. But who knows? So let's start by building a simple circuit with just one resistor in it. Or maybe two resistors in series. All right. And we're going to measure the current, the potential across them. Let's we'll build it. I'll draw it out for you as well, and then we'll kind of make a prediction as to what we'll measure, and then we'll measure. All right. Here's the breadboard. Right. This is kind of the base that you're going to use to build circuits in here. And the way these work is there's kind of a power strip along the side here. You might be able to, let me zoom in a little bit. You can see there's a plus here and a minus here, right? This row is all connected to each other. If I go down here, everything on this column is all connected to each other. So if I put, if I take my positive terminal for my power supply, I'm going to put, this one's red, so I'm going to use a red wire just to kind of flip it in here and stick it in here. All right, so now, right, I have this, right now my power supply is at 4.6 volts. I'll set it to 5 volts just to be nice and even. Whoops. Anyway, so basically now every hole in here is at positive 5 volts. And if I take the, how many black wires now? Brown. Take my negative terminal. And I'm going to stick it really anywhere in this second column. I don't want to put it right next to that one, but it doesn't really matter. I'll put it down here. Right, but the important thing is it's in this negative column here. Right. So now every hole here is at positive 5 volts, and that means every hole here is at 0 volts. Right. So I can begin my circuit from here. This is the positive terminal. And when we get over to these middle ones, they go by rows, right? So every row 1 here, these 5 holes are all connected to each other. These 5 holes are all connected to each other, and so on. These 5 holes and these 5 holes. Right? So we can build a circuit from that, and you'll kind of see how it goes. The important thing to remember here is kind of this is the power strip. The column, this column is connected with itself. This column is connected with itself. And then this is where we're going to stick our resistors and capacitors when we get to that, and light bulbs. And we will remember that these 5 holes, there's probably a better word for it than hole, but these are all connected to each other. And stop me if something you can't see something, or if you have any questions. I do have my speaker turned up. Okay, so let's build a circuit with a couple of resistors in it. Let's see, I've got I should probably use bigger resistors because I haven't kind of thought about this ahead of time. And the bigger the resistance I use, the smaller the current. I don't want to blow anything up. Here's a bag of 4.7 kilo ohm resistors, and here's a bag of 10 kilo ohm resistors. So this is my 4.7 kilo ohms, right? 4.7 thousand ohms. Let's start with one. Let's start with one resistor in the circuit, and then we'll see. We'll see if we can make any predictions about that. So, all right, a couple wires. I'm going to take a wire and jump from the positive terminal to, let's say, heat. I want to do it so it's as kind of as clear as it can be. So I'm going to go from the positive terminal here, right, to this row where it kind of fits in at row number 3 here. Zoom in a bit more. All right. So what I've done now is I've made sure that this row number 3, where the orange wire goes to, that's at positive. Let me make sure I'm on autofocus. Okay. This is at the positive 5 volts now. This whole, all these holes here are at positive 5 volts. I'm going to take my resistor, the 4.7 kilo ohm resistor. Right now it's connected as well because this hole is connected to that hole. And I'm going to connect it down to, wherever down here. Row 18, wherever it fits. All right. So my circuit's almost connected now, right? I've got from my positive power supply to the positive power strip, to row 3, to this resistor, to row 18. And what's the last thing I need to connect to make this circuit go?
Your negative to row 18.
Yeah, I got to connect negative to row 18. But you know what? I'm going to do one more thing. I want to put a switch in here. Make it a little bit. I do have switches. Did bring switches up. Here they are. So you're right that I would complete the circuit by going from row 18 to my negative strip, but instead I'm going to go from row 18 to this switch. I should have put this. Okay, here's what I'm going to do. I'm going to get a couple of I'm going to get an alligator. Good thing I have a full 5 minutes before the next class to clean all this up. All right. So I'm going to take this out for a moment. Or I'm going to unclip my negative, and I'm going to clip my negative terminal to this switch here. All right. And I'm going to clip this end of the switch back to the negative terminal. And I'll try to make it so you can see it in a second. All right, you see what I did there? So now the negative terminal goes to this switch that I can open or close. When it's closed, the circuit's running, right? Because it connects now to my negative power strip. When it's opened, then the circuit's broken. Okay, I know it's not very easy to see. All right. So I do want to keep the switch in the screen a little bit. Here we go. All right. So now the last thing that I want to connect up on my circuit is from row 18 to the negative end of my power strip. So let's do that. Take a jumper wire. Anywhere in row 18 is fine, right? Because they're all connected. And anywhere on the negative strip is fine because they're all connected. You just want to kind of. All right. So now, if I close the switch, the circuit will run. But before I do that, how am I going to know if it's running? Right? I can put my finger on it and see if I burn myself, but that's not the best way. I'm going to put a what do I want to do first? Put a voltmeter or an ammeter? Let's put an ammeter. Let's measure the current. All right. So what I'm going to do, if I want to measure the current flowing through a circuit, I've got a device called an ammeter that measures the current flowing through it. Am I going to put the ammeter, if I want to measure the current, do you think I'm going to have to put it in parallel with the circuit or in series?
In series.
Why do you think that?
At least from what I got from the homework last night, if you're looking for the current, things are going to be completely different depending on like the voltage at that point. Well, you'd only have one resistor, but I think since resistance is when it's in parallel, it'll be 1 over R, and then like it's the inverse. I think just being in series will be better because it's not like you don't have to screw with things like that. It's just the value itself, if that makes sense.
Yeah. So, right. Well, the idea is if when we talk about the current in a loop is always the same, right? No matter where we go around in the loop, right? If we put something in parallel, now we've got 2 loops, right? So if the ammeter, some of the current then will go through the loop with the ammeter in it, and some of the current would go through the loop with the resistor in it, but we wouldn't have so we might know how much current's going through the ammeter, but we wouldn't know how much current's going through the resistor, right? It's got to be in series. So let's see. I've got my ammeter here. I've plugged in my leads. Let me put this here, move this a little bit. And I want to turn the dial. So if I want to measure current, let's see. This will measure voltage, right? These are units of volts. This is AC voltage. That's why it's got a sine wave. I want to set it here, 200 milliamps. That means that this can measure current up to 200 milliamps. If I go larger than that, it's going to blow the fuse. And I don't know how easy the fuse is to replace in these. I do have fuses, but I hope we don't have to blow it. This one, it has a 10 amp limit, but we have to use a special different connector for that. And there's no fuse. I don't want to do that because it's real easy to kind of break the device if you go over the 10 amps or even use it for a long period of time. So we're going to try to keep it to low current so as not to break anything. I have exactly 10 of these, exactly enough for one for each of you. So 200 milliamps is what we're going to set this to. Right, and right now there's no current flowing, so this is 0. So I'm going to put this in series, which means I'm going to take this one out. So I'm going to put, and if I got to make sure I do it. If I do it the wrong way, I'll get a negative current instead of a positive current, and I can switch it. But I think it's the red one that I should put in the higher potential. So I'll put this. This isn't very good. All right, I'm gonna have to use a clip. So I'm clipping the lead here to row 18. So I'm going to put this in series with the circuit, right? So now in row 18, I've got, so now after the resistor, right, the current's going into my ammeter, right? And then from the other end of my ammeter, so after the current passes through the ammeter, I'm going to clip this to not row 18, but another row down here. Doesn't matter where. Let's put it in near the end. This I'm sorry if this is hard to follow along, but just you know, you'll get a chance to do this pretty soon. So just good to see it a little bit. All right, so now what's happening is we've got the positive power supply, 5 volts here to the positive power strip. That positive power strip is connected to row 3, where it's connected to the resistor, which goes to row 18, which is connected to the positive side, I hope, of my ammeter. Then the negative side of my ammeter is connected to row 27 or so. Back to this clip, which I need to now put to the this is the ammeter to row 27, and now we can make my last connection go from row 27 back to the negative end of the power strip, and then I should have a complete circuit. Let me do that. Row 27 to the negative strip. No current yet, right? Because I still have the switch open. Can we do a quick calculation? Let's see. I've got right now my power supply is set to 4.8 volts, and I know I used the which resistor did I use? 4.7 kilo ohms. How much current should run through a circuit with 4.7 kilo ohms of resistance and 4.8 volts? Let's calculate that real quick and make a prediction. See if you can do that. Take a minute. One resistor, 4.7 kilo ohms. Our delta V is 4.8 volts. Right. And we know that R equals or V equals IR, so I equals V, I equals V over R. Right? Our current is going to be delta V over R, which is 4.8 volts over 4.7 kilo ohms, which should be about 1 milliamp, right? 4.8 over 4.7 thousand should be about 1 milliamp, a little bit less. Or a little bit more, right? 1.02 milliamps. It's always good to do the calculation first because you can make sure that you're within the limit, right? I don't want it, if I have more than 200 milliamps, you know, this whole thing will explode or just get hot and melt my fuse. So that's what I expect, about 1 milliamp, 1.02. Is that, yeah, thanks. I see, I just saw your chat now. Yeah. See how we get that? Okay, so now I will flip the switch and this should go up to 1.0, and it's in units of milliamps, right? So this is 1.0 milliamps. And that's it, right? I can, nothing much else is happening except there's one milliamp of current flowing through here. It's not even getting warm yet. It's not a lot of current. Okay. And then I open the switch and the current goes away. All right, so far so good. Questions, comments? What do you think the resistance needs to be inside of an ammeter? Inside of an ammeter, do we need to have very, very high resistance or very, very low resistance? Or does it matter? Very, very low. Why? Why low?
I think it's because you're trying to measure the raw, like well, the raw input from a different circuit. So you can't have anything inside the ammeter to affect what you're trying to measure from the other circuit.
Yeah, that's a right idea, right? What would happen if there was what would happen if the resistance inside the ammeter was another, was also something like 4.7 kilo ohms?
Then you'd have even a lower current.
Yeah, that would change my equivalent resistance in my circuit, right? Instead of 4.7 kilo ohms, I would have to add the other, it would be double that, right? And that would change the current. Right. So you would if you put I put my ammeter in series with the current, if there was a decent amount of resistance in there, that's going to change everything and it wouldn't be a very good measurement, right? So you really want almost no resistance in the current. What would happen if it was a super high resistance, 70 billion ohms?
Then you just wouldn't get a current. You'd get a very, very, very low current.
Yeah, you'd get a tiny, non-measurable current, right? So the circuit wouldn't work. So an ammeter's got to have very, very low, close to zero as possible resistance. Otherwise, you're going to block the current. You're going to change it, right? Because it's in series. Okay, why don't I next? Why don't we next look at the voltmeter, right? We want to see how the voltmeter is going to work. Voltmeter now I'm going to take out here's what I'll do. So for safety, you don't want to work on the circuit while it's running, right? So if I'm going to take anything out or put anything in, I want to make sure I have the switch open. We always want to have a switch. It's really for safety. And it's fun to go like this and turn it on and go like that, but mostly for safety. No, mostly for fun. So let me take my ammeter out. Right, so now my circuit is completely right now there's a gap in the circuit between row 18 and row 27. Is this one big enough to bridge it? So I'm just going to put a wire in there. So now I've got the same circuit as before. I just don't have the ammeter in there. So I'm not going to be able to measure it when I turn it on. Right, I can still turn on my circuit. There's still going to be 0.1 milliamps. Right, we just don't know that that's happening. But I want to measure now the potential difference across the resistor. So if my delta V in my battery, right, so let me draw this circuit real quick. And this is an ideal battery, or it acts like an ideal battery. And I still have this at what is it? Oh, it's 4.8 volts. So I've got this. Sorry, but this is such a. All right, I've got this, right? Delta V is 4.8 volts on my battery. I've got a 4.7 kilo ohm resistor. If I want to measure the potential difference just from here to here, let me do a point A and a point B. What would I expect the potential difference here to here between point A and point B? If we assume all these wires are ideal.
Wouldn't they add up to be the same potential difference as the battery?
Yeah, exactly, right? This is the same, this location here, A, is the same potential as the positive terminal. This location, B, is the same potential as the negative terminal. So yeah, so the potential difference, if I measure the voltage across the resistor, I should get the 4.8 volts that the battery is. All right. So do I want to put this voltmeter in parallel with my resistor, or should I put it in series like I had the ammeter?
I think series again.
Well, if I put, okay, so if I put it in series though, right? So let's say, so let me adjust this real
Wait,
quick.
no, if you put it in series, I think it's only going to give you the chance difference between.
So
I'm not sure.
yeah, this when we measured the current, right? This is the ammeter, right? We put the ammeter in series, and it measured the current flowing through this part of the circuit, right? And it's one loop, simple circuit, so the current was the same everywhere. But when I measure potential, I want to measure between 2 points. So if I threw a potential, if I wanted to measure the potential here, right, I'd be measuring the potential, from this point to this point, if I put it in series. And the potential from this point to this point, in our circuit should be the same, right? Because it's, an ideal wire. So point B, the potential is going to be the same as all the way over here at the negative terminal.
Yeah, I see. It needs the 2 points to get the potential difference. If you put it in just one side, it's not going to give you. Yeah.
So voltmeters ammeters always go in series, right, and measure the current through that loop. Voltmeters always we want to put in parallel, right? So it's going to be something like this. Okay, so I need another branch, and I can, whether I connect it close to the resistor or close to the negative terminal doesn't really matter, right? This is an idealized circuit. We just want one end of the voltmeter to be before the resistor, the other end of the voltmeter to be after the resistor. Should this voltmeter have inside the machine, inside the voltmeter, is this going to have a high resistance or a low resistance? The voltmeter itself.
Would you want a high resistance because you're looking for the volts between those 2 points, or?
We do want a high resistance. What would happen if this was a low resistance? What would happen if the voltmeter had a smaller resistance than this?
Wouldn't it just be the? I'm assuming you'd probably blow the fuse because you're sending a lot of voltage through the voltmeter, or?
Well, yeah. So
wouldn't it like short circuit or?
Yeah, because you're putting all that current through. Well, it acts like just one resistor technically because it's all over one, but you still that second branch would basically short circuit because it's no resistance if you had no resistance.
Right, the current wouldn't be going. So if there's no resistance here, right, the current's not going to go through where the resistance is. The current's going to go through where no resistance is. Right. So not only are we making a short circuit, you're right, we make a short circuit here, but we're not getting an accurate measurement of the potential anymore because because the current's going through this branch instead of this branch. Right. When we make a measurement, we don't want to affect the circuit, how it works. Right. And you can't technically do that perfectly well, but you can do it good enough.
How much resistance would it need?
Well, it needs to have a lot higher than 4.7 kilo ohms. Right, enough so that the equivalent resistance, when you do if you do 1 over 4.7 kilo ohms plus 1 over the voltmeter, and then take the reciprocal, you still have 4.7 kilo ohms.
Is that why you changed the switch in the voltmeter depending on like how high the voltage? Oh, I see.
Yeah, you have to change the switch because you need it. I mean, really we want infinite resistance, right? Mm-hmm. And you can get pretty close to infinite resistance. It's just not you have an insulator in there. So yeah, exactly. That's why we need to change the switch. And inside the voltmeter, there's going to be high resistance. So let me turn the switch. We expect it to be, well, I've got my power supply set to 4.8 volts. So it should be 4.8 volts. So I'm going to set this to, if I set it to 2 volts, that's not going to be good enough, right? Because that's the maximum. So I'm going to set the next one up to 20 volts. All right. You understand that, right? This is the reading here is going to max out. And the reason there's different ones why you don't always just set it to the highest one is because you can get more precise measurements, right? If you've got a really tiny amount of voltage, the 20 volt thing has 2 decimal places after it. If I go to 2 volts, I can do it to 3 decimal places. So you basically want to go, what voltage are you going to have and go to the next setting higher than that.
Sir, is there a reason why there's 2? Like they go by increments of 2 and then it goes to.
Oh, you mean why it's 200 instead of 100?
Yeah,
different different voltmeters will have slightly different settings. I don't know if there's I've seen ones that aren't always 2. It's just I guess just the how they manufactured it.
I see.
The fact is, you know, the important thing is that like this one is kind of 10 times bigger than this one. This one is 10 times bigger than this one, right? So you kind of have a few orders of magnitude of voltages that you can measure. All right, so let's see. Let's connect the voltmeter in parallel to our resistor, right? I've got the positive terminal of my voltmeter here connected to this. So I'm just going to put this also in row 3, right next to my resistor. All right, so now the current is going to be able to, it's branches, right? The current can flow through this resistor, or it can flow through this branch. But we know our voltmeter has a nearly infinite resistance, so no current's actually going to flow through that branch. So the same amount of current's going to flow through the resistor, whether or not we have the voltmeter there. So I'm going to take the negative end of my voltmeter and put that, where should I put the negative end of my voltmeter?
On the end of the resistor.
Yeah, at the other end of the resistor, right? And it shouldn't really matter. So I can put in row 18, but it doesn't really matter if I put in row 27 as well, because those are the same potential. But technically, but yeah, let's put it right at the end of the resistor here. So there we go. All right. Now my circuit's still open. The switch is still open, so it's still reading 0 voltage. When I close the switch, I hope it says right now my power supply, if you can see it, 4.8 volts. That's the potential difference between the positive strip and the negative strip there. So when I close the circuit, I should also get, and I have an extra decimal point here, right? So this is actually a little more precise than my, so I'm, you know, it might be 4.77 or it might be 4.82. Let's see, closing the switch. Hey, 4. I think I guessed that right, didn't I? So 4.82 volts, right? Exactly what we would expect.
Wouldn't we expect it to be less than the one from the battery because of the resistance in the wires?
Yeah, so the resistance in these lengths of wires, it's not quite 0, but it's so small compared to 4.7 thousand ohms. I mean, these are going to be tiny fractions of an ohm in each of these.
Oh, I see.
Right. So 4.70001 kilo ohms isn't gonna change anything. But you're right. I mean, if we used really long wires that had a resistance that was at least comparable, then yeah, then that would happen. Mm-hmm.
I see.
That's good thinking. Anything else about the voltmeter circuit that we have here? That's this circuit here. I wasn't sure how this was going to go, but it seems like it's working, at least that you can see what's going on here well enough. Okay, so why don't we do something next? Why don't we look at, we're going to put we're going to add something else into this circuit. I'm going to add an LED bulb, and I don't know what the resistance is of these LED bulbs. So let's see, and if I blow one up, that's fine. So I'm going to put an LED bulb in series here, right? And for now, I'm going to leave the voltmeter here. So I'm going to measure the potential across this same resistor, right? And I know the amount of current flowing through the resistor and the LED bulb is going to be the same, but I'm going to have a different equivalent resistance for the whole circuit, right? I'm going to have 4.7 kilo ohms plus whatever the resistance here is. Let's call this R. So I'm going to leave my power supply at 4.8 volts. If I put a resistor in series here, what's going to happen to the reading on the voltmeter? Increase, decrease, stay the same? Can we predict it exactly? Let's see. What color do you like? White, red, blue, yellow, green?
Blue school.
Yeah, blue is good. All right, so let's take one of these. So if I look at these, right, I've got 3 different blue resistors. All 3 can handle currents up to 20 milliamps. And that's good because I only ever have 1 milliamp. You know what, if I do it, it might not be bright enough. Well, that's all right. We can pump up the voltage. And it tells you about what voltage is good for it to be a reasonably bright, bulb. And I don't know how ohmic these LEDs are, right? They might be slightly different resistances depending on on the potential. Okay, and we'll do a lab actually. One of the things that we're going to do is figure out if these are ohmic, if the resistance changes or not as we put different voltages across it. So I'm going to take this one.
Mister, so resistors like do their job by changing current into heat energy, right?
Yeah. Yeah.
So that means light bulbs would change it into, well, LEDs specifically because they convert it to light very efficiently.
Yeah.
They convert it into light instead.
Yeah, exactly. An incandescent light bulb will convert it into both, right? Light and heat, not very efficiently. An LED does a much better job of not converting into heat and using much more of that energy to go into light. That's right. So
it's basically like a resistor, but it just acts usefully, I guess. I don't know.
Yeah, it is. It's a resistor that I mean, resistors are useful in circuits, but you're right. Instead of turning the energy into heat, it turns the energy into light, which can be more, which is useful. You guys know what LED stands for?
I thought I did, but I forgot.
Light emitting diode, right? Light emitting makes sense because it emits light. Diode is a circuit element that current can only flow through it one way, right? The way this is, we don't need to get into why. But light can only, or current's only going to flow one way. So you see how one end of this is a little bit longer than the other one? We have to make sure that the longer end is at the higher potential. If we put it so that the shorter end is at the higher potential, no current's going to flow through this. It's basically going to have effectively infinite resistance. The current can only flow one way through a light emitting diode or any kind of diode. That's what makes it a diode. Okay, so what I'm going to do here, I'm going to leave my voltmeter where it is. I'm going to pull out this. Let me see. I don't have a. Pull that out. Remove this one. Let me remove that blue one as well. How are we doing on time? Do you know what time this class ends? I have no idea.
11:15 apparently.
Okay, thank you. All right, and I'm going to switch this to beam over here. So my circuit's broken now, right? I still have basically what I've removed is this wire here going from the end of the resistor back to the negative terminal because I want to stick my oops, sorry. I've kind of removed this piece here and I want to stick the LED in. All right, so I've got this. This is the positive end, the longer end. So I'm going to put that here on row 18. And the negative end, it looks like, is getting stuck in row 22. So now I just need to connect. Still in row 22 there. Now I just need to connect row 22 back to, is that right? Back to the negative end. And then I still have my voltmeter is measuring the potential across the resistor, but not across the LED. All right, nothing's flowing yet. My switch is still open, but I've got this circuit now. I got the voltmeter is still measuring just the potential difference across here, but not across here, right? So remember, remember how, you know, in the analogy that we talk about with, you know, water flowing through a pipe, right? The battery is the pump, right? It pumps it from, you know, 0 feet at the bottom up to 4.8 feet. Flows along here, then we have a potential drop, right? In our first circuit, it dropped all the way back down to 0 going through the resistor. Here, it's not going to drop all the way back down to 0 because it's still got some height left here, right? And then it's going to drop down to 0 after this one. So that means I should see, and I don't know what R is here. It might be, well, hopefully it's big enough that we see something happen. But instead of getting the 4.82 volts, it should be smaller, right? Because now it's not dropping all the way down until it gets to the end here. If I put my voltmeter after the LED, so I'm measuring from point A to, let's say, point C, and we'll do that. It should be the same as the battery, right? Because point A is the same as the positive terminal. Point C is the same as the negative terminal. But point B now isn't the same as either one. It's somewhere in the middle. All right, so let's flip the switch. We'll see if there's enough current flowing. I don't think there is. I don't think it's going to light up because I don't think 1 milliamps enough to make it light. A little bit. Can you see that it did light up a little bit? Yeah. Okay, I got 2.26. That's good. That's actually right about what I was hoping. Actually, and now would be a good time for the lights actually to go out so you can see it does look blue. It does, and in person, it looks like an LED, but it doesn't look quite as bright as an LED usually looks. But you can certainly see it going on and off, right, when I flip the switch.
Yes, we can see.
So 2.26 volts, that's what I'm reading, right, as my potential difference between A and B. So what's R? What's the resistance of that LED? How do we find that out? And if we can figure out R now, what the resistance in the LED is, I think we're good to stop it there for today. So take a moment and think about how we can find R.
Do we have the current?
We can measure the current, but we can figure it out without doing that. We could stick an ammeter somewhere in our loop, and we would definitely be able to do it that way, yeah. But we can do it just by knowing that this potential, I'll call it VAB, is 2.26 volts.
Are you measuring the potential from the resistor or?
Yeah, across
where's
the resistor still, right? So really the voltmeter, one end of it is before the resistor, the other end is between the resistor and the LED.
Oh, I see. It's between. Oh, so it's before the LED. Okay.
Yeah. So if I were to put the voltmeter instead, then let's start with an easier question. If I were to put the voltmeter instead between point B and C, and I'm not going to do that just yet, what should the voltage read if I measure between points B and C?
It should read whatever you have on the voltage meter now minus the 4.8.
Yeah, exactly. And right. So if I did 4.82 minus 2.26, and I'm going to use a calculator, because why not? Right. So 2.56. That should be the potential difference. So this should be my delta V minus VAB equals 2.56. Right. My delta V is 4.82. So that potential should be 2.56 volts. So how can I calculate R?
Well, with the voltage and we already know, like, if you take the resistance, you can do the. I think this is a similar problem. If you do the try to solve for equivalent resistance,
Mhm.
you can then try to solve for current, and then you can solve for just the resistance of that that bulb. I think.
Yeah, I think you're right. I don't think we need to, I think we can do this without figuring out the current.
But yeah, because the current is going to be the same.
The current
Yeah.
should be the same. Well, is it going to be the same 1 milliamp that we had before?
No, it won't because
No.
you have a different
The same across the entire circuit.
Yeah.
Right. It is going to be the same across the entire circuit. So we do have an I. We're not going to measure it. We don't know exactly what it is. We'll be able to calculate it, and maybe I don't think we'll have time to check it. But let's see. I know that the equivalent resistance is going to be 4.7 kilo ohms plus R. I also know that the delta V is going to be I times the equivalent resistance, right, throughout the whole circuit.
So that means the resistance is going to be proportional to potential difference, basically.
Yes, right. If this was exactly 2.26 volts again, then we would know the resistances are exactly equal. Yeah, they're not exactly equal, but you're right. It's proportional to the potential difference across them. That's right. So let me write that out as an equation here. That means that we also know that 4.7 kilo ohm. Hold on. Uh-oh, I lost my train of thought. How do I write this clearly? So I know that delta V over I, that's my equivalent resistance. Sorry. Right. Equals 4.7 kilo ohms over I. That's the resistance through, oops, sorry. Why am I drawing a blank right now? Yeah, let's just look at it proportionally. I don't know why I'm we can say that the resistance, oh look, now you can see the light a little brighter now, the overhead lights went out, right? All right. Okay, anyway, we know that the resistances are proportional to the potential difference. So the resistance of the resistor, so 4.7 ohms, kilo ohms, over the potential from A to B that we know is 2.26 volts, equals the resistance of the bulb over the 2.56 volts. Right? They are proportional. And I'm sorry I didn't. I'm losing it right now. So I haven't done it from here. But 4.7 kilo ohms over the 2.26 volts equals R over the 2.56 volts. So let's real quick, we can calculate R is going to be 2.56 times 4.7 kilo over 2.26. Yeah, so and I get 5.323. So the higher is that, or yeah, I think that's right. So it looks like I get an R of 5.3 kilo ohms. You can confirm that, I think, if you do the calculation. So that means, and that sounds okay to me, because we know that the bigger the resistor, the more the potential drop is going to be. So we have a slightly higher resistance on the LED than we do on our resistor. So we have a slightly bigger potential drop, 2.56 across the bulb, than we did across our resistor, is 2.26. All right, so we got a 5.3 kilo ohm resistance here in the LED bulb, and it would be interesting to see if we changed the voltage on our power supply so it wasn't 4.8 volts. We know we change everything, but it would be interesting to see if we still have 5.3 kilo ohms in the bulb. If we do, if no matter what the potential difference is, if we still get 5.3 kilo ohms of resistance there, then we have an ohmic material, and it's ohmic, and it follows Ohm's law. If it doesn't, then it's non-ohmic material, because the resistance changes depending on what flows through it. And you're gonna do a lab. You're gonna test that out. Are these LEDs ohmic or not? Okay. Any last questions, concerns about this? I have recorded this one, so I'm going to put this up. This will be considered the lecture about voltmeters and ammeters, because that's what we really need to know, that voltmeters have very high resistance so that no current flows through that branch, and they would put them in parallel. Ammeters have very low resistance, so they don't block the current flowing through, because they're placed in series, right? That's the kind of short and sweet what we need to know about voltmeters and ammeters. All right. I cannot find the stop recording button. Oh, there it is.